In our last class, we discussed about one of the very important topics of group, subgroup, and we explained how this is defined. So, idea is suppose we have a group, say G is a group and H is a subgroup. So, as you understand that normal subgroup, so by definition, by default, H is a subgroup and it should satisfy some extra property. That's why the normal term came into picture. So, what does it mean? It says that we have suppose G is a group of this kind of operations, say with respect to dot. Then in our last class, we have defined what do you mean by G of H. That means it's a collection of sets G dot H such that H belongs to H. That means you are multiplying all the elements of H with G from the left, and that collection is known as GH. Okay, so they are known as cosets. Similarly, we can also have this H into G, that is all such element H multiplied with G. So this dot is the operation of G such that H belongs to H. So this is known as left coset since we are multiplying it from the left, and this is known as right coset since we are multiplying it with from the right. Okay. Now, if it happens in our last class, if you have a look at this in our last class, we did this kind of calculation. So it was a detailed calculation. So we took H1 to be like this. H1 was a subgroup of say two elements. H1 was my this E and 1 2, and for this H1 we calculated this the left coset. So here this dot means the composition of elements. So here you can see that E dot E, E dot 1 2. So they are basically the collections of left cosets. So what we see that if I multiply it with by E from the left with H1, then suddenly it gives me back H1. So that was my H1. Okay. So they are the all left cosets of H1 in G. And you see that we could find three different types of left cosets. Maybe E12 one type. Here also we get E12 and then 1 3 and 1 2 3. So here you see that this is a different type, but again 1 2 3 1 3, the same type here, and here also we get the same type 2 3 and 1 3 2. Okay, so what you see that here the number of distinct left cosets were 3, though we are multiplied from the left with 6 distinct elements, yet finally as a set we get 3 distinct sets, though it gives you 6 sets, but ultimately if you look at carefully we ultimately get 3 distinct uh, sets. Okay, so 3 distinct left cosets. Similarly, if I take this H1, the same H1, and multiply it from the right with the all elements of S3, we again get 6, initially 6 right cosets, but if you look at carefully, then you see that out of these 6 right cosets, exactly 3 right cosets are there. 3 distinct right cosets. Okay. So that is the meaning of left cosets and right cosets that we have already seen in our last class. Okay. Now then, what is the importance of this normal means? Normal means if it happens that if G dot H equal to H dot G, for all G belongs to G, then we call H to be a normal subgroup of G. Then H is called a normal subgroup of G. Okay. So what happened if we instead of taking 1 2, so this is H1 was my E and then 1 2, instead of taking this, see here in this property is not satisfied. For example, we have seen that many cases, so 1 3 into H1 is not same as H1 into 1 3. In our last class we have already checked this. Okay, but instead of taking H1 as this, if I consider another subgroup which was my H4. So H4 is nothing but our alternating group A3. That means E 1 2 3 and 1 3 2. So if I consider this, then we see that for each cases, all of them are equal. E H4 equal to H4E. Similarly, 1 2 into H4 is same as H4 into 1 2 and so on. So in that case, you see that for all left cosets and right cosets for a particular element, they coincide as a set. Okay. So this group has this property GH4 equal to H4 into G for all G belongs to S3. So as a result, we can very easily say that this, so this group is a unable to accept him. Okay, could you please tell him to try again? Somehow I am unable to make him join. Okay, not sure why it's happening. Anyway, so that's why you say that you see that this property is satisfied. As a result, as a result, our, so what we can say, so this property is satisfied for that group if I consider G to be S3 and my H to be A3, same as E 1 2 3 1 3 2. Okay, in that case these properties are satisfied, and as a result we can see that A3 is a normal subgroup of G. Okay, yeah. আচ্ছা রবীন্দ্র, কে লাস্টে এলে? রবীন্দ্র, রক্তিম লাস্টে এলে নাকি? কে লাস্টে এলে বলো তো? আচ্ছা এবার থেকে একটু তাড়াতাড়ি আসার চেষ্টা করবে, ঠিক আছে? So we see that A3 is a normal subgroup of G. But if I consider our H1, then H1 was my E and 1 2 is not a normal normal subgroup of G. Okay. So you understand, to check whether a subgroup H is normal or not, we need to check this. But this is a kind of set property. So can we check with respect to some elements? So today, first we are going to show you a very important theorem that are usually used to check whether a subgroup is normal or not. So you can think of this is as a theorem. It says that let G be a group and H be a subgroup of G. Then H is normal in G if and only if for all G belongs to G and for all H belongs to H, G H G inverse belongs to H. What it says? It says that H is normal subgroup of G if and only if for all G. That means if you draw like this image, if you draw like this, so G is a group and H is a subgroup. So that is given. Now it says that take any element from G and take any element H from H. If it happens that for all G and for all H, this expression is always within H, then we call H as a normal subgroup of G, and the converse is also true. That's why this is if and only if result. As a result, When we will check whether a subgroup is normal or not, usually we go for this approach. So let us try to prove this. Okay, how to prove? So first, let us assume that H is a, so H be a, so let's so let us assume that H be a normal subgroup of G. Then what does it mean? Then for all G belongs to G, GH equal to, what should I write here? GH should be equal to somebody?
HG.
Very good, HG. And this is true for all G. So what I need to prove? I need to prove that GH, G inverse belongs to H for all H belongs to H. So to prove GH, G inverse belongs to H for all H belongs to H, right? Okay. So first have a look at this. So what you need to show is that somehow this element, this expression should be in terms of only an element of H. Then you will be able to say that this happens. Okay. So the only problem here is, okay, first have a look at this. So as GH equal to HG, what do you mean by this? As an element, there exists H1, H2 belongs to H such that G of H1 equal to H2 of G. First, you note this one. So this is a set. This is a set. Two sets are equal. Then what do you mean? Suppose this is one set. So in our last example, if you see that, so these two sets are equal. Suppose these two sets are equal. Say this one and this one. Okay, let's, yeah. So this set and this set, they are equal, right? What does it mean? That means this element is same as this element is same as this element, and this element should be same as this element. It is not correct. The correct statement would be this element should be same as some element of this. For example, see, 1 3 and 1 3 is same, the first position is same, but here I had 1 2, but here I have 2 3. That means here this element, if these two sets are same, what does it mean? That this element must belong to this set, and you do not know the position. Okay, so here also, if I have this set equal to this set, so one element from here should look like G of H1, and one element should be from here should look like, say, H2 of G. So they are equal means there must exist some H1 and H2 such that they are equal. Okay, is it clear to all of you, this statement? And that will be somewhere sometimes very much required if we deal with this kind of sets. Okay, so is it clear to all of you? Good. The expression is GH G inverse. Okay, so it consists of GH. So have a look at what is GH. So GH must belongs to GH. So GH must be within this element because H belongs to H. As a result, G dot H must be within this set. And what is this set? This set is same as HG because it was our hypothesis. GH is same as HG. Then what does it mean? That means GH must be equal to sum of H1G for some H1 belongs to H. Is it clear now? If you understand this step, then this step is trivial. Okay, so GH G inverse equal to, what is this GH value? GH is same as H1 G G inverse. And what is this value? Is E. So H1 into E, and this is H1. And where this H1 belongs? H1 belongs to H. So this belongs to H. So what we need to prove? We need to prove the same thing that we just now proved. So started with G inverse, GH, G inverse, GH, G inverse, and ultimately at the end of the proof we have shown that that is within H. What does it mean then? Then this statement is proved. So we started with the fact that H is a normal subgroup, and ultimately we have proof that GH, G inverse belongs to H for all G belongs to G and for all H belongs to H. Now the other part. So here what we need to assume? So conversely, let for all G belongs to G, for all H belongs to H, G, H, G inverse belongs to H. What do you need to prove? To prove H is a normal subgroup of G. Normal subgroup of G. That is, to prove for all G belongs to G, GH equal to HG. Right? That we need to prove. Okay. So somebody, let's try. So this is a set and this is again a set. We need to prove this set is same as this set. So how to start with? Somebody, can you tell something how to start with? How to start with? Can anybody tell me? Anybody tell me? Okay, so what we need to prove, GH should be equal to HG, and this is a group. So both of them are groups. So what we start with, take an element from here. So let GH belongs to G capital H. Okay, that implies, what do you mean by that? That implies GH. What is that meaning? GH. How do you prove this? Any guess? Any guess? So what we need to prove? We need to prove that GH equal to HG. That means this element. So we need to prove, if we write it in a detailed way, then we need to prove GH belongs to HG. Just you need to switch these two elements. GH should be equal to HG kind of thing. That will be sufficient. Now you can understand that GH, you can write it like this, GH, G inverse, and then what is extra here? G is extra, so you can put G like this. So by associative law, GH, G inverse into G. Now according to your hypothesis, for all G belongs to G and for all H belongs to G, H, GH, G inverse must be belongs to H. That means this belongs to where? H into G, because this belongs to H. So that implies GH belongs to capital H of G. So you started with this belongs to this, and ultimately you have shown that GH belongs to HG. So what would be your conclusion? Anybody? What would be your conclusion?
GH is subset of
GH is a subset of HG. Similarly, you can prove that. Similarly, you can prove that. You can prove that HG is also a subset of sorry, here I think I have done some mistake. Yeah, yes. So it should be GH. So that's why it should be GH. Similarly, we can prove that GH is also a, oh, sorry. Uh, it was, so ultimately what we proved? Ultimately, we proved GH belongs to, that implies it was a wrong statement. Okay, so let me again restate this one. Okay, I'm just repeating once again. So we started with GH belongs to GH. We need to prove that GH belongs to H of G. Okay. Now, how you can write GH as a GH, G inverse, and as an extra, you can multiply it with G. So it becomes E. So GH will remain GH. So that belongs to. Now, as per the given condition, this is within H. For all G belongs to G, for all H belongs to H. So as a result, this belongs to H of G. So what do you proof that we started with GH belongs to HG, we finally, sorry, we started with GH belongs to GH, and we finally proved that GH belongs to HG. As a result, GH is a subset of HG. Similarly, you can prove that H of G is also a subset of GH, and that implies HG equal to GH. And that's what we needed to prove the final statement, because that then if you able to prove that for all G, this is true for all G belongs to G, that will in turn imply that H is a normal subgroup of G. So that's the normal definition of normal subgroup. So we started with this statement and finally we proved the converse one. So what is this statement then? It's very important statement to prove whether a given subgroup is normal or not. We just need to check, take any element H from H and take any element G from G and check whether G inverse belongs to H or not. That's all. So that will finally give you your required answer. Okay. Is it clear to all of you? Any question till now? Okay. So next, let us try to find the application of this. So check. Uh, just okay. Maybe here we have already seen that. So H was our A3, H4 was our A3, and you can check whether that is a normal subgroup or not. You have one way of checking this, but you can also check with all elements of G and all elements of H. Okay, but that will be mostly required while proving some other theorems that will come into play maybe after a few classes. But for the time being, let us have a look at another very important result, which says that let G be a group, and H be a subgroup of G. Then, okay, let G subgroup of G means G dot. Okay, then AH equal to BH if and only if A B inverse belongs to H. Note that it's just a subgroup. I'm not talking about normal subgroup, but what I say that, so this is, if I have a subgroup, then you can always have a quotient notation. So AH and BH are quotient notation. So usually I should put a dot here for proper understanding, but you will understand that when you will be matured enough, then this dot will not be required. From the context, you have to understand what do you mean by this dot. So if this is, instead of, if this would be plus, then this statement, can you tell me what could be this statement? If I consider with plus, then what should be
A
this
plus
statement? Very
A
good.
plus
A
H
plus
equals
h,
to B plus H.
b plus h, if and
If and
only if.
only if A minus B belongs to H.
Very good. So now you can understand that depending on this plus and dot, this condition will be changed. Okay, it may be arbitrary star, then a b inverse with respect to that star. Okay, so whether this statement is true or false, that is my question.
Sir, this is actually false, I think.
Can you give an some example? So now it would be a interesting topic to discuss. So a h equal to bh, if and only if you can prove that b inverse a belongs to h, that could be fine. So instead of writing this, if this is b inverse a, then you have no problem, right? But will that be
Yes, sir.
okay? A b inverse, will that be fine? A b inverse, will this statement is true or false? According to you, it is false. Now the question is, then you need to give me some example. Is it clear to all of you?
Sir, here we can, as AB inverse belongs to H, then BA inverse, this also belongs to H, and this is for all AB, so we can interchange these two. So,
How? No, this is not true for all, right? This is a particular a and particular b. So up to this is fine. Then B inverse A of whole inverse must also belongs to H, because H is a subgroup. So all the elements inverse is also within this. And what is this? I am sure that you have already seen that this is A inverse of
B.
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 So I think you all know that if A B inverse is B inverse A inverse, that you all know, right, in group theory. So that means A inverse of B inverse of inverse, and that is B. So A inverse B belongs to H. That part we
H.
have done. Yeah. Now, then how to prove A B inverse? So that part we have already seen, that A inverse B within H. Now we need to prove A B inverse is within H, and that too we don't know whether that is true or false. That is the discussion that we are now currently doing. Somebody says that that is false.
স্যার যদি H নরমাল সাবগ্রুপ হয় তাহলে
If
লেগ
H is a
প্রসিডার
normal subgroup, then it's fine. But I'm talking about it's only a subgroup. I haven't mentioned anything about a normal subgroup. If H is a normal subgroup, then it's fine. But if not, then what will happen? So can you write by some means A B inverse equal to A? No,
Sir,
this should be B. Yeah.
sir, if G is S3 and
Yes. If G is S3.
H is E comma 1 2.
Okay. The last example. Good. Let's
Yes.
see.
Then
Okay. Let's go to this example. So your, yes. So yeah. So this
uh,
H1 is 1 2.
yes,
Yes.
and then 1 3 H equals to 1 2 3 H.
1 3 H. 1 3 H is basically 1 2 1 2 3. Yeah. The same as,
1 2 3 H.
yes. 1 2
Then
3
if
H.
we consider A to be 1 3 and B to be 1 2 3, then
Yes.
A B inverse is coming to be 3 2, which isn't in H.
Very good.
So we get a counter example.
Very good. So now it's clear. The statement is false. Okay. So let us again have a look at this. What she has pointed out. Let's start with the statement AH and BH if and only what I wrote initially. AH equal to BH if and only if A B inverse belongs to H, and H was a subgroup, any subgroup. So what she gave, G equal to S3 and H is my this group E12. Okay. In our last class, we have seen that they are same. 1 3 into H, 1 3 into H is same as this one 1 2 3 1 2 3 into H. In both cases, they came as 1 3 1 2 3 1 3 1 2 3. Okay. Now, if this statement is true, then if the statement that I made was AH equal to BH if and only if A B inverse belongs to H. If this happens, then so here this is my A and this is my B. Then A B inverse. What is that? 1 3 1 3 2. And what is this? 1 goes to 3, 3 goes to 1. This is so 1 goes to 1, 2 goes to 1, and 2 goes to 2. So 2 goes to 2. Sorry. 1 goes to 3 and 3 goes to 1. So it becomes nothing. Then take, say, 3 goes to 2 and then 2 goes to 2. So 3 goes to 2 and 2 goes to 1 and 1 goes to 3. So sorry, 2 goes to 1 and 1 goes to 6. So 2 goes to 3. So this one. See, this is not within H. So you get a counter example. That's why in our last class, this will give you lots of information if you just write it down in a proper way. That's why I kept it to give you lots of examples that will be required for your basic understanding. Is it clear? So what we wrote was not correct, but what you proved was correct. So instead of proving this, if I prove this one, and that will in turn give you A inverse B. So for left cosets, this property is satisfied. AH, if and only if instead of writing this, A inverse B belongs to H. Let's check if this is happening here. Okay, so this is my A and this is my B. So A inverse B, what is this? 1 3 and then B is, so inverse of A is 1 3 and inverse and B is already there. So 1 2 3. Let's check what is this. This is 1 goes to 2 and 2 goes to 2. Okay, and then 2 goes to 3, 3 goes to 1. What is happening? 2 goes to 3 and 3 goes to 1. So 2 goes to 1, and that is also not here. Is it correct? 1 goes to 2, 1 goes to 2 and 2 goes to 2. So 1 goes to 2, 2 goes to 3 and 3 goes to 1. So 2 goes to 1. Okay, then what is happening? And 1 2 is not within this set. 1 2, okay, 1 2 is within H. Yeah, so 1 2 is within H. So it's happening perfectly. Okay, so if we have left inverse, then left coset, then the idea will be it should not be the correct statement. The correct statement should be A inverse of B belongs to H. Clear? So I have seen many students, they actually get confused what to write because they only read and may not do the proof. Unless you do some proof with some counter example, then it will be really difficult to remember whether it is A inverse B or A B inverse for left cosets. Okay, so the actual statement would be, the actual theorem will state like this: theorem, let G be a group and H be a normal subgroup of G. Sorry, be a subgroup of G. May not be normal. Yeah. Then AH equal to BH. If and only if, what should I write? It should be, it should be, somebody, it should be, what
A
should I,
inverse B belongs to H.
A inverse B belongs to H. So one part I have proved, if they are same, then A inverse belongs to H. Now try to prove the other way around and you can prove this. If A inverse B belongs to H, then you need to prove AH equal to BH. Okay, what you need to prove? The converse. I think you will able to prove the converse one. So what we need to prove here? So initially what we have assumed? We have assumed that AH equal to BH, and we proved that A inverse B belongs to H. Now what we need to prove? Conversely, let A inverse B belongs to H. We need to prove AH equal to BH. So as the set approach, so this is element of AH. So it's a set. So AH belongs to small h to show AH belongs to BH. Note that somehow from AH to BH, so AH is not containing B. So AH is not containing B. So somehow you need to incorporate this fact with the help of this statement. Okay, hope you will able to do. If not, then from here some new thing may come up that you first try to prove on your own. If you are unable to prove that after lots of effort, then something new came up just now you have already witnessed. So this is, so that is a kind of usual mistakes by the students. But the what will happen for right cosets? So it's for left cosets. And what will happen if I have this statement HA equal to HP, if and only if, what should be the statement? Okay, so this is your homework, so please check it. So this is your homework for both left cosets as well as right cosets, for both left and right cosets. Okay, now we come to again another very important aspect that you have, I have already started discussing that, but maybe with again great detail. Okay, so let G be a group, maybe let G dot be a group and H be a normal subgroup of G. Okay, let us define a binary operation star on G quotient H. So what is G quotient H? This is the elements of this form such that G H belongs to, sorry, such that G belongs to G. So if I consider only one G multiplied with H, then that will give me one left coset. So this is a left coset. Now if I vary all G belongs to G, so then this is the collection of what? This is the collection of all left cosets of G in H. So this is nothing but the collection of all left cosets of H in G. Note that in, so why I didn't talk about this is the set of all left cosets of H in G. Note that when we consider GH, in our last example, when we consider GH, we found only three types of left cosets. Though we multiplied with 6 elements, ultimately we got only three different types of left cosets. That's why this is called collection. That means the same entity may appear many times. For example, here the same entity appeared two times. That's why this is collection. So that is, naively speaking, collection and set. The difference between collection means the same entity may occur many times. But if I consider A, B, C, then we usually do not consider this as a set, but we may term it as a collection. That's why, as you understand that if you vary G, then it may happen G into H might be same for 2G, same G. I mean two different G of H may be the same, like here. So for G equal to E and for 1, 2, we got the same set, E12 and 12E. The set wise they are same. That's why this is the collection of all left cosets of H in G. Okay. Now we define. So let us define a binary composition on G. So then this binary composition star is a mapping from where to where? Somebody tell me. It's a mapping from. So I want to define a binary composition on G. So binary composition should be a mapping from where to where? Anybody? From? So if I ask you the question, suppose star is a binary composition on G. What does it mean? Star is a mapping from where to where?
G cross
Cross G to G.
Very good. So if I ask you the question, define a binary operation star on G, that means it's a mapping from where to where? It's a mapping from where to where?
G star G to G.
Not G star. So G quotient H cross G quotient H to G. We call this as quotient. So G quotient H star cross, I mean this is the same cross G cross H to G cross H, right? So this is the binary composition defined by, now I need to defined by, so here some element should look like, how the element should look like here? G dot H. So I put it say G1 dot H, and how the this element should look like? G2 dot H, and you are applying star on it. That means G1 dot H star G2 dot H. After some time I may drop this notation star, I mean dot. Okay, from the context it will be clear. Now what does it mean? Yesterday I have defined. Do you remember this? How do I define? So what are the, yes, Very good. So what are the operations that you have? You have only dot within G, and G1 and G2 are the element of G. So you can combine these two elements only with dot. You cannot combine with star because star is defined on a set, right? And then the same dot into G, because this is an element. So now this is also a left coset, right? Because this is an element, G1 dot G2 may be G, and then G dot H. So for all G1H, G2H belongs to G quotient H. We call it G quotient. Why this is quotient, you will be understanding shortly. G quotient H, not G by H. So please remember, this is not G by H. We call it G quotient H. So many of the students, they say that this is G by H, but technically speaking, it should be said as G quotient H. Okay. So I claim with respect to the star defined on G quotient H, G quotient H star is a group. Okay, that we are now going to prove. Okay, so for that, first we need to check few things. Okay, again I am going little bit deviating from here to a very simple thing. So you all know the definition of a function. So you all know what do you mean by a function. So say function f from one set to another. So you all know what do you mean by function. Okay. Now suppose this is my set, only set, say z5, and say this is my set z10. Okay. Now I am defining something. I am not talking about whether I am defining a function, but I am defining a very interesting thing by like this. So the element should look like some class of something. So class of 5, and here also it looks like class of 10, right? Now I define like this: f of class A of 5 should go to f of A of 10 for all A5 belongs to Z5. For example, if I consider f of say class 2 of 5, then it should be class 2 of 10 here. You can understand, class 2 of 5 means it is an element of Z5, and class 2 of 10 means it is an element of Z10. Okay. Now question: is f injective, surjective? What will be your answer? First, let us check whether f is surjective or not. Is f surjective? What do you think?
No, sir.
Why not? Why not? So subjective, somebody says no. True or false? Somebody says false. Why false?
Thus, at class 6 of 10 has no pre-image, like class 7 of 10 has no pre-image.
Okay, so you got some logic to give the idea that this is not subjective. Is it injective?
Yes, sir.
Yes, sir.
So injective, you all mention that this is true. Okay, so everybody agrees this fact? Any deviation? So if not, then let us come to an interesting idea. Okay, so when we define the mapping, if it's on a finite set, say A, B, C, and let's say again A, B, C. Suppose I have defined like this: A goes to A goes to B, C goes to B. Sorry, again say this. Will that be a mapping?
No, sir.
Why not?
So A goes to two elements, A and B.
Okay, so here it looks like A goes to A as well as A goes to B. So according to you, from the definition, it is not a mapping, right? Okay, so it's not even a function, not a function. Function and mapping are the same thing. Now again relook. So it was my Z5 and it was my Z10. Okay. Now consider class 0 and class 5 in Z5. What is the relation? What should I write here? Greater than, less than, equal. What should I write here?
Equal.
It's equal.
Equal.
That this
Okay.
is
Well,
not a mapping.
okay. Now consider f of 0 of 5 and f of 5 of 5. What should it give according to the definition? It should give 0 of 10. Give. It should give 5 of 10. Are they equal, greater than, less than? What should I write here? Equal, not equal? What should I write here?
Not equal.
Not
Not
equal.
equal.
Not equal. So from Z5 to Z10, class 0 equal to class 5 goes to class 0 of 10 as well as class 5 of 10. So what is your conclusion then? Conclusion? What is your conclusion? Will that f be function?
No, sir.
No, sir.
F
Not.
is not a function. So f is not a function, but you have already developed that f is not injective, I mean f is injective and f is not surjective. But the basic fact that f is not even a function. Okay, so that are the many interesting facts that are involved in mathematics that usually it gives you a kind of illusion. So if I ask you in that way, if I teach you this first and ask you this question, you will certainly give me the other way around. But I just show you on the other way around and I forced you to give me the answer, wrong answer. But unless I do it like this, you won't be able to remember those things. So that's why the teaching way should be in a different way, that where the students usually they are confused or they get give the wrong answer. So now it's clear to all of you. So this property is known as well-definedness. Well-definedness. So a mapping should be well defined. That means, so what do you mean by well defined? Well defined means if A equal to B, that should imply FA should be equal to FB. Though it looks quite trivial, but you can understand that you all are fooled with a very simple example. So not always this property is very easily checked. That's why it is required to check whether a function is well defined or not, and then you need to do more things on it. Okay, why that had problem? First, let us have a look at why this element has a problem. The problem came due to the fact that the same element can be represented in many ways. Like 5, I can also have 10, I can also have 20. The same element, the representations are different. As a result, you can understand that as a result, it may give you a confusion. So if this kind of scenario happens, then it is always recommended to first have a look at whether the function that are given to you is well defined or not. Okay, so this is an important fact, and that happens when usually we deals with this kind of quotient. Now you can understand that just now we have seen that two of them are equal. Say just now we have seen that, say, G1H equal to G2H if and only if G1 inverse G2 belongs to H, right? Just now we have seen. So you can see that in this case, it may happen that two of the quotients may be equal. Then if you define some function, then you need to show that this function is well defined or not, unless you are doing so. Here you may have different, the two sets may be same, but after giving f, this may not give you the f of G1H, may not give you f of G2H. So as I mentioned in my last class, here you will certainly able to find that kind of function where you will able to understand that if you define star, as just now I have mentioned here, the star, if I define star in this way, then if you consider your H to be like this, H1, that means E12, you will able to show that if you define star like this, star as just now I have defined, you will not be able to, so this is a function, right? Then you will be you will able to show that star is not well defined if you consider H to be, if you consider H to be E and 1 2 in G was my S3. But here note that I consider a normal subgroup. That is very, very important. This well definedness will always be there if you consider H to be a normal subgroup. Note that E12 was not a normal subgroup. But if this normal subgroup, if you assume that H to be a normal subgroup, then suddenly the property will be satisfied and you will be done. Okay, so that's why this normal subgroup plays an important role here. Firstly, unless you have this normal subgroup, you won't be able to define the well definedness property if you multiply, if you define the star in this way. So now I will going to show you how this forms a group. So to show that this forms a group with respect to star, that means to show that this quotient H, sorry, to show that G quotient H with respect to star is a group, we need to first show, we need to first show star from G quotient H cross G quotient H to G quotient H is well defined. That means we need to show, what we need to show then to show that this is well defined, that means take two elements from here. So if I look at the similar idea here, what we need to show that take two elements from here, A and B, suppose A and B are equal, to show that FA should be equal to FB, right? So here you need to take two elements from here. How the elements should look like? The element should look like this. Two elements means, say, A1H comma A2H, say A1H comma B1H, say. So this is an ordered pair. Like in coordinate geometry, you have might have done this at 2. How the element should look like in two dimension, A comma B. So here also the cross product is basically, you will get it more detailed when I will teach you this product, but for the time being you can understand that the element should be an ordered pair here, right? And another element, it should be same as another element, say A2H equal to B2, sorry, A2H comma B2H. Okay, clear? Now what you need to prove? So this is my A, this is my B, and they are equal. So what you need to show? To show the function, here the function is star. That means star of A1H comma B1H should be equal to star of A2H comma B2H. What does it, this star means? Star of this means, that is to show star of this means A1H star B1H should be equal to A2H star B2H. That is to show how I define this star. That is to show A1 into B1 into H should be equal to A2 into B2 into H. That means you need to show that if this is happening, then they are equal. And why, how they are equal? Suppose in your coordinate geometry A comma B is same as C comma D. What is your conclusion about AB, the relation between A and B, C and D? What is your conclusion? How they look like? What is your conclusion? Suppose they are equal. Then what do you say? A equal to C
Equals
and
to C, B equals
B equal to D. Very good. So if they are same, what is your conclusion then? Then A1H equal to A2H and B1H equal to B2H. So that is given, and that should imply that this should be equal to this. So if you are able to prove this, then you are basically able to prove that star is well defined. Is the motivation clear to all of you? We need to prove, here that if they are same, then this happens. Okay, so how to prove that? So what you understand, that somehow this A1 and B1 has to be transferred into A2 and B2. So you can understand very easily that A1 and A2 are related through this H. And just now we have done a bit of this. If they are equal, then how can be written like this, and so on. So somebody tell me how to do that. Anybody came out with some idea?
স্যার একটু চেষ্টা করবো
Okay, sure. Okay, so you have already done? Yes, please tell me.
আচ্ছা তো এইচ A1H ইকুয়ালস টু A2H তো কোনো স্মল
Yeah,
h1
please
আর
in
স্মল
English.
h
Please in English. Yeah. H1H equal to A2H. Yes.
then for some small h1 comma small h2 belongs to capital H,
Very
we
good.
get A1H1 equals to A2H2. Then if then A1 should be equal to A2H2 H1 inverse.
A2 H2 H1 inverse. Very good.
And then যেহেতু B1H equals to B2H, then we can
B2,
similarly write
so B1H equal to B2H. That implies B1
B1
is also
into
equal to, say, H3 H, say,
huh,
H4
H3 H4
H3
H3 inverse.
inverse. Yes.
Then if we compose A1 from right side,
Okay, for some, just a minute, for some H3, H4 belongs to H. Okay, then,
if we compose A1 from left side,
okay, so what we need to show, they are same.
A1 B.
Okay, just now we have shown that AH equal to BH if and only if A inverse H equal to, sorry, AB inverse A inverse B belongs to H. Just now we have shown, right? And I have shown you that it should be A inverse B and not B inverse. Clear? So to show this, what we need to show? We need to show basically A inverse. That means A1 B1 inverse, right? Into A2 B2. If we are able to show that this belongs to H, then we are done basically. Okay, then how to proceed? Then what to do? That's what you told, right?
Yes, sir. I say that in the second equation, if I compose A1 from the left side,
Okay, second equation means this one. So this is your
yes,
equation 1 and this is your
yes,
equation
yes.
2. Okay. Okay, I will follow your whatever you tell, I will write. Okay. So from equation 2, yes. What should I
A,
write?
A1 B1 equals to
A1 B1
equals to
equal to A1 B2
B2 H
B4.
4 H.
Okay. So H4 H3 inverse. Very good. Then
Then we put right side the value of A1.
value of A1. A1 is A2
A2 H, small h
A,
for the
H2.
H to H1 inverse. We let H equals to H to H1 inverse.
Okay. And then say V2 H4 H3 inverse. What you say that this is an element of H, so I can put it H simply
Yes,
here
H.
and maybe here some H1
H dash.
H dash. So that will be H2 H V2 H dash inverse and H dash. Okay, yeah. Then
But J to H is a normal subgroup.
yes,
Then so
well,
HB2 equals to B2H for all H for all small h belongs to capital H.
what H
HB2 equals to B2H for all small h belongs to capital H.
no since okay, but you are almost right. You since H is a normal subgroup of G. What do you say?
B2H equals to HB2.
B2H equal to HB2 for all H.
No,
No,
sir,
that
no, sir.
is
For all B.
for all B. For all C. What it should be like B2 capital A should be H of B2. That's why I told. So this when it comes, it this H and this H may not be the same.
Yes, sir.
So if you write H equal to H1 B2, then it's fine. Or maybe H5, already H1 I have used. You understand? So your
Yes,
statement
sir.
is not correct. So please modify your statement. So you are doing quite well. Good. Then what should I write? Up to this is fine. Then what should I write? So what is your aim? First, you first decide what is your aim, what you want to show. Say A1 B1 equal to, then what you need to prove actually. You need to show this, right? What do you need to show?
Yes,
You need,
sir. We can compose H dash inverse. Then we
okay,
can compose H dash inverse from right side of the equation.
okay.
Then we get A1 B1 in H dash inverse equals to A2H B2.
So from 3, right? This is your 3.
Yes. Yes.
Okay, very good. So if I do like this, then it will be A1
1 B1
B1
H dash
plus
inverse
inverse equal
equals
to
to A2 H
H
B2.
B2. Very good.
Then we can place H B2 such as B2 H double dash.
Very good. Now your statement is correct. So as H is a normal subgroup of G, H, sorry, H, I can write it, H B2 belongs to capital H B2, right?
Yes, sir.
That is same as B2 capital
H
H,
double dash.
because that implies H B2 should be equal to B2
B2
H
H
double dash for some H double dash belongs to capital H. So we can put it.
Yes, sir.
That is equal to
A2
A2
B2 H double
B2
dash.
H double dash. Okay.
Then
Now you see
it
that,
is proved.
yes. So yes, it is proved. Yeah, but yes. So what you say, just one more step. If I made it like this, this was your, if I multiply both side with this, so what I get, A1 B1, maybe say some say okay, H dash inverse equal to A2 B2 H double dash. We get it, right? Now if I multiply with both side, first by A1 B1 inverse on both side, then what we get? We get A1 B1 H dash inverse equal to A1 B1 inverse A2 B2 H double dash. So now I am again multiplying both side by H double dash inverse. Then how, what should, so this becomes E, right? Then H double dash whole inverse into H dash inverse equal to A1 B1 inverse A2 B2, and that belongs to capital H because this part is within H. Now what this will imply, just now we have shown here, what is this meaning? If A inverse B belongs to H, what we will say? AH equal to BH, that means A1 B1 H equal to A2 B2 H, and that we needed to prove. A1 B1 H equal to A2 B2 H, and just now we have proved. Very good. Now is it clear to all of you? It looks quite messy, but the idea is very simple. You just need to replace one by another just to get this answer. Clear to all of you? Any question? Any question? If you have, please do not hesitate to ask me. Is it clear to all of you? Okay. So what we proved is star is well defined and the remaining things are quite easy. Associative and all the remaining things can be proved quite easily. What do you think the identity element? So G quotient H, then it could be easily proved that this with respect to star associative, because this is actually defined with respect to G dot, right? So since this is associative, it is not very difficult to prove. Okay, let us try to prove. Say G1H star G2H star G3H. Remember, I just dropped this dot because now you are matured enough to prove that, I mean, to understand that in between the dot is there. What is that dot? That dot of this G. Now this is same as, by definition, G1 dot G2 H star G3H, and what is this? This is G1, G2, G3. That means in between dot is there of H, right? Now if you consider bracket here, will that make any change? G2H star G3H. Okay, what will this value? G1H star G2 G3H. I am dropping the star or dot in between, and then by definition G1 G2 G3H. So you can understand both the values are same, so this is associative, and this is true for any G1H, G2H, G3H belongs to G quotient H, so it is associative. So what do you think, that who will be the identity element here? Who will be the identity element here?
H.
Very good. So E dot H, and in our last example you have seen that E dot H, what it gives? It gives you basically the original H1 back. So actually the formally writing E dot H should be the identity element, but that is same as H. So this is the identity element. Identity element of G quotient H. Now let GH belongs to G quotient H. Tell me what would be the inverse of GH inverse. What would be the inverse of this? What should be the inverse of this?
G inverse H.
Very good. G inverse H is the inverse of this GH. Okay. So now tell me, if I ask you this question, is G quotient H commutative for any group? Is G quotient H commutative? True or false? What is your answer? Let me check. Is G quotient H commutative?
That if G is commutative, then G quotient H is also commutative.
Very good.
And
So this is in general false because I consider G to be any arbitrary group. But if G dot is commutative, then G quotient H is also commutative. I hope you understand the proof, because G1H star G2H equal to G1 dot G2H, and since G is commutative you can write it G2 dot G1H, and that in turn give you star G1 of H for all G1 H G2 H belongs to G quotient H. So what is your conclusion then? The conclusion is, if this is commutative, then G quotient H is commutative. Okay, if I ask you this question, if G is infinite, will G quotient H be always infinite? True or false? What will be
No,
your
sir.
answer?
Infinite set can have finite cosets. Maybe.
Example?
Uh,
Sir, Z quotient to Z.
Very good. So if I consider G to be Z, and since this is a commutative group, any subgroup of G is also commutative, right? So any subgroup of G is a normal subgroup of G, as Z plus is a commutative group, commutative group, any subgroup, any subgroup of Z plus is a normal subgroup. We have already proved it in our last class, is a normal subgroup of G. Okay, so you can have the quotient. Okay, so we have like this. And with respect to this addition, now this addition, how this addition is defined, how the elements looks like. So first element, say n1 plus 2z is first element. It was dot, remember it was dot in my last example, but now I am dealing with plus. And if I again write the plus, note that this is a set, and I am considering say n2 plus 2z, but I am using the same plus. Note that the same plus is not same as this plus. So this is plus of sets, but this plus is basically element addition with the element of 2z, that means integer plus, but this plus is different. But now you are matured enough, that's why we can use the same plus. Okay, then how it should be defined? Quickly tell me, what should be this value?
n1 plus n2 plus 2z.
N1 plus N2 plus 2z. Okay, now with respect to this addition, as just now we have seen that this is a group, and since Z is commutative, as a result this is a commutative group as well, right? Okay, now the question is how many elements does it have? Okay, so just now we have seen that if A and B are, say if A plus H equal to B plus H, if and only if A inverse B belongs to H, if and only if minus A plus B, so this is A inverse and this is plus B belongs to H. Okay, now how many elements does it has? Okay, does it have, how many elements does it have? Any idea? Do you think how many elements that it should contain? Okay, suppose I put 0 plus 2z. What should be the set? This is
2z.
2z. Very good. If I consider 1 plus 2z, what should be this set? Again 1 plus 2z. But if I write 2 plus 2z, what should be this case?
2z.
So 2z.
2z.
Because 2 plus 2z is same as 0 plus 2z. Why? Because minus 2 plus 0 belongs to 2z. Minus 2 is an even number, so it belongs to 2z. That's why 2z, 2 plus 2z is same as 0 plus 2z. So that is 0 plus 2z. Now what's about 3 plus 2z? What is this value?
1 plus 2z.
1 plus 2z. Because 3 plus 2z is same as 1 plus 2z. Why? Because minus 3 plus 1 equal to minus 2 belongs to 2z. See, all the things that I am using, very simple thing. That's why I emphasized on this particular result. People, they may miss this result, actual result, but the actual result is this. So you can understand now this. There you have only two different types of cosets, whatever with the value of n. So either even or odd. If it is an even number, it must be equal to this. If this is an odd number, then the quotients will be like this. So if you vary n over all z, then also you will get only two different types of elements. So So how many elements are there in the cosets? Either 0 plus 2z or it should be 1 plus 2z. Nothing else. That's why the number of elements of that group is finite and it consists of 2. Similarly, you can consider, for example, Z quotient, say 101Z. How many elements it will have? What would be the order of this? What should be the order of this?
101.
101. Okay. So now it's very easy for you to guess. So the number of elements of the quotients are, even if the group is infinite, the quotient may contain finitely many elements. So G quotient H may contain finitely many elements. Okay, the last thing today I'm going to do is again very exotic. So R3 you all know, R3, the three-dimensional with respect to addition is a group. So it's a commutative group, commutative group. So any subgroup is a normal subgroup of G. So R plus is a normal subgroup of R3 plus, right? Now, how this should look like? Any geometrical interpretation of this group. Note that this plus and this plus, they are not exactly the same. But now you are matured enough. That's why I put the same plus. Okay. But understand that this is for addition of real numbers and this plus for the quotient of two quotients, addition of two quotients. But I am giving you the same notation. Now try to understand what should be the geometrical interpretation of this quotient group. How this R3 quotient R should look like. So R3 means a three-dimensional like this. Some x-axis, y-axis, z-axis is there. So this is my x-axis, this is my y-axis, and say this is my z-axis. Now tell me how this should look like. R3 quotient R. So this is my whole R. And what is R? Can you tell me what is R with respect to this image? What is this R? How should I represent R in this diagram? Anybody?
R can be x-axis or y-axis
Very
or
good.
Line on
z-axis.
R3.
So for the timing, I tell say x-axis. Okay, it could be x and it's minus x. Now tell me how this should look like. So do some analytics here. Say R3 quotient R. How the elements they look like. So there are some ordered pair of elements. How they should look like. Okay. Now
So
instead of,
R1,
sorry.
sir, will it be like this R1 into in bracket R1 R2 comma R3 comma R4.
Okay, I will come to it later on. Just a minute. Instead of doing this, first let us have a look at how this looks like xy plane. I think it would be easier. Xy plane. Instead of R, I am quotienting it with respect to xy plane. Can you tell me in geometrically xy plane should what should be the xy plane? What is the xy plane? What is the xy plane here in this? So this flat, right? So this is my xy plane. So xy plane is nothing but R2. So this is R2. Now if I quotient with this xy plane, how geometrically it should look like. So now it's xy plane. How they should look like. Okay, so R3 means some ABC plus xy plane. How the xy plane looks like? So, okay, maybe I should write it here. So R3 quotient xy plane. So some element from R3, say A, B, C plus xy plane. How it is a set, not a point, collection of points. Some x comma y and z coordinate is 0, such that xy belongs to R, right? Like this. So if I add all the ABC with this, how it should look like? And you should vary this ABC over R3. ABC belongs to R3. Why? Just remember G quotient H, how it should look like. It should look like GH such that G belongs to G. So here, this is my G, this is my H, such that this G belongs to whole G. So ABC belongs to R3. Okay. And how it should look like? It should look like, if I add them up, then it should look like A plus X, comma B plus Y, comma C, such that, so it will be like set of this, such that xy belongs to R. That means you are varying xy, and then again such that, so this is your coset, such that A, B, C belongs to R3. So you need to vary all over R3. Now, geometrically, can you think of how this looks like? How this looks like? Okay, so I will give you this as a your homework to think. Think properly, geometrically. Unless you are good in
Sir, a
geometry,
plane parallel to XY plane.
very good. So this means a plane or a collection of planes which are parallel to xy axis, xy plane. What he gave is a correct answer, and please always, all of you must agree with that by convincing yourself. Unless you can see those things, it would be really difficult for you to do good in abstract algebra. So here things are very abstract, so you need to understand it. But once you are capable of thinking things, then it's very easy. Okay, just think about this. What is this? For a fixed ABC, so you need to vary. Think about, for a fixed ABC, what geometrically it should give, and then vary ABC, then what should it look like? So what I gave a name of this. I call it infinite bread. Infinite bread means our pauruti. What it says, that if this is so the bread is a three-dimensional, right? So it is basically a slice. Slices are there one after another. Few slices are there one after another. But in R3, we have a special property that any between any two real numbers, you have infinitely many real numbers. And since you are varying C all over the R, that's why there will be infinitely many planes which are parallel to our XY plane. And if we could have this infinite bread, then the whole world will not have any food problem. Because in between any two bread, you can always find another bread. That means you can never be end up, or you can never be uh, devoid of the breads. You can always have breads. So that's why I name it as infinite bread. It looks like it's a all the seats. So you can think of all the braids, they are basically lying parallel to the XY plane. And since R is dense, I think you have already heard about the term dense. So between any two real numbers, you can have infinitely many real numbers. As a result, if you vary C over R, you will get infinitely many such planes. So it will be like infinite bread. Okay, if you are not quite comfortable what I told you just now, just try to visualize this, try to draw the image, try to draw this, and then you will able to understand why I'm saying so. And if you're able to understand this, then it's quite clear that you are very good in abstract algebra as well as geometry. So if you are not able to understand, please try to think it, and when you get it, you will be able to master in abstract algebra. So that's my point. So that's all that what I want to say today. So if you have any question or comments, please let me know. I will try to answer your queries. Anything?